Welcome everyone for the second edition of the new Technologies in Mathematics seminar for 2025. Today it's our pleasure to have Frida Simon from Oxford tell us about datasets for mathematics. So Frida, take it away.
Okay, thank you very much for having me. Can everyone see my screen, just to make sure before I start?
Yes, we can see your slides.
Perfect. So just a quick background from where I'm coming from. I'm both a computer scientist as well as a mathematician, and hence my strong interest in mathematical data sets and getting something that is hopefully a math co-pilot within the next few years. And at the same time, I'm working as the AIMO prize manager, which is this Kaggle competition to incentivize people to create better language models that solve Olympiad level problems, but I'll speak more about that in general. So this talk, I'll be essentially focusing on my latest preprint on data for mathematical copilots, but a few other papers will also make their appearance as I speak. And there are essentially three ways that you can talk about AI for mathematics. So one way would be the sampling way. And there are two papers that highlight this on the left side. And this essentially means you generate with computer software a bunch of textual representations of mathematical objects. And then you learn, typically with supervised learning, a relationship between them. And you hope to get some insight out of this relationship that you see. And a very early article that illustrated this was a deep learning for symbolic mathematics one back in 2020 already, where they showed that you can essentially learn integration. And a more interesting one was one a bit later about knot theory, where they also learned a relationship and showed that you can actually glean a new mathematical relationship from this statistically learned relationship. So this is one way that is primarily based on sampling. Then there's another way that is based on searching. And a typical preprint that illustrates this is the one by Wagner that essentially uses reinforcement learning in a formal mathematical environment. And then there's, of course, the talking way that I'll be mainly speaking about now that is very much based on datasets, unlike the other two approaches. And for datasets, I kind of distinguish between different eras of datasets. And initially, I think we had something that was what I would call the tentative era, because it wasn't really clear at that time whether the language models would ever get to a stage where they would be able to solve mathematical problems in a way that is actually useful for us. And during this phase, datasets were typically datasets that had easy problems, math word problems, and it kind of started around 2015, 2016. Datasets were quite large already at that time. The Dolphin 18K dataset already had 18,000 data points, but all in all, they were pretty simple. And this was followed by what I call the standardizing era. And this era really kind of kicked off in 2020, still before ChatGPT, and its most representative two data sets are the math dataset by Hendricks and the GSM8K dataset. And these have become somewhat of a standard. So anytime a new language model is released, one of these two datasets or both will appear in the benchmark that comes with the model release. And GSM8K has been solved already for quite a while now, and more recently math has been solved as well. Most of the datasets that are being released now score very high on math. It's essentially a solved dataset by now. And interestingly, the GSM8K dataset was, I believe, released slightly after the math dataset in 2020. And one of the reasons they released that dataset was that I've quoted here from the GSM8K paper, these two excerpts, where they said that if we extrapolate from current trends, we will require an exorbitant parameter count to achieve even a moderate performance on distributions as challenging as the math dataset. So GSM8K, even though it was released later, thought math was too challenging, but only essentially 4 years later, I think last year in spring sometime, the Gemini model by Google got over 90%, the math specialized one. So 5 years later, the dataset was essentially done. And now we've entered a modern era, I would say, that is characterized by a large number of datasets on mathematics that are being released. And these data sets cover all kinds of mathematics at all kinds of levels. So we moved significantly beyond the, I would say, high school level mathematics that all the previous data sets were focused on. And we've kind of explored various other facets of mathematics, other difficulty levels. But all of these data sets at the same time are of a certain type. They are all more or less math word problems. Sometimes they're asked about theorems, but even in this case, they're of the type, can you show, and then some statement follows. And essentially, we want from the language model a solution or a proof, which works really well already. One example from the math data set is one that GPT-4 can solve easily. And this is now what I will be exploring in the next few slides, this type of math data set that is focused on these math word type problems, even if we can reach quite high levels of difficulty. And difficulty in these data sets can essentially be split into two types. So one type of difficulty is where the proof gets really tricky. And these are typically problems from Olympiads and data sets that focus on Olympiad level problems, where the abstraction level is low. You don't really need to know a lot about mathematics, but you need to be able to confidently manipulate the involved mathematical objects. You need to be able to see relationships between them, and you need to have a large bag of proof techniques to be able to solve some of these problems. The other category in terms of difficulty is abstraction, where you have layers of definitions. And when you want to solve a problem, it often involves either unpacking various definitions or understanding the relationships between the different objects and different definitions. And this is also hard, but it's hard in another way. Of course, you can merge these two, but for now, most data sets are of the first type, where we focus on tricky proofs and less about more advanced mathematical objects. And the problem that I've quoted here, which is from the AI Math Olympiad, where we have 10 reference problems, is actually quite a funny problem. And what I'm showing here is an excerpt from our forum that we have on Kaggle, where this problem doesn't just create problems for language models, it even creates problems for humans that are participating in our competition. We have the solutions, they're publicly available, and even though they're online and everyone can read them, they're really hard. You have to really focus even to understand the solution, and sometimes people don't even believe our solution. So even in this case, the contestant acknowledged that the solution said the final answer was 79, but was still not sure why it wouldn't be 99. So hard problems, even if they don't involve abstraction but tricky proofs, can be very challenging. And in terms of abstraction, this also creates problems for language models, where in this case, I'm showing below a data point from the GHOST dataset, where a language model tries to solve this problem from Rudin's exercise and gets it wrong. And this is something that I'll also return to a few slides, just as a teaser for now. And the AI Mathematical Olympiad currently, I would say, is really the pinnacle in terms of assessing how well language models do in terms of tricky problems and problems that require tricky proofs, but low levels of abstraction. And this competition is sponsored by XTX Markets. I'm managing it at the moment. The problems that we have are Olympiad level problems. We have, for the first competition that ran last year, problems that were of a difficulty level that was below the AIM competition. And this year we have problems around a difficulty level that is roughly a national level math Olympiad. And this is so AIMO 2 is currently ongoing, it's running. And both AIMO 1 and AIMO 2 started in autumn and have run, respectively, will run until spring, with the winner announced at the AIMO. And the answer in this competition is a number between 0 and 999. That means contestants submit their language model to Kaggle. The language model is evaluated on half of our data set. So out of the 100 problems that we have, it's evaluated on 50. And at the end, the language model has to return a number. So we can easily match the accuracy, how many problems the language model solved, simply by checking if the right number was output. And after the competition ends, all language models will again be re-evaluated on a different set of 50 problems that follow a very similar distribution in terms of difficulty, because we have some slight variations among problems, and also domain, because we have different types of problems, number theory, geometry, and so on. And then the final winner will be evaluated. And in terms of AIMO 1, we can see this is a screenshot below from the end of the competition. And we had a team that's called Numina that won, who achieved 29 problems out of 50. This was, I think, on the public leaderboard, but I think on the private one, they scored very similarly. And AIMO 2 is currently ongoing, and I'm just showing you here on the right a screenshot from the problem that I previously mentioned that created difficulties even for humans. So you can see the solution is quite long and somewhat involved. And for now, the race is tight. Although we have already exceeded the performance of the previous competition, so even though there's still 1 month to go for AIMO 2, the public leaderboard winner attained a score of 32 problems, which is more than the winner of the entire AIMO 1 competition, which kind of shows just how much language models have evolved in a single year. And it's interesting to actually see who's competing in this competition. So Nemo Skills, the currently #1 ranked team, is composed of some researchers from NVIDIA. The second team is a Kaggle Grandmaster. Third team is a team, I think, of students, perhaps also a professor from the ETH in Zurich, Switzerland. Number 4 is comprised of students from Tsinghua University, I believe, as well as researchers from Microsoft. And the number 5, again, is a student competitor. And number 6 is also interesting. He's a person who competed in the famous Netflix prize. I think this was back in 2006 and was, I think, part of the winning team. So we have quite a diverse selection, I think, or interesting selection of people that are competing. And we can ask ourselves, okay, we have these competitions. They're currently evaluating language models on really, really hard mathematical problems, at least when it comes to proof difficulty. But what really is the benefit of running these types of competitions? And one immediate benefit is they incentivize to create better open source language models. And in the case of Project Numina, they released the 7 billion tool integrated reasoning model. It's publicly available. And this is quite a nice solution, because what it does is it takes a statement for a problem that it has to solve, and it translates it to Python code. And of course, they didn't devise this model from scratch. They built on the DeepSeek math model and did some really, really clever fine-tuning. And yeah, on the right is a picture of part of the winning team where Terence Tao gives them the prize at the AIMO last year in Bath. So that's one thing where the competition helps to incentivize, create better language models. Another useful benefit of running these competitions is dissemination of information about what training methodologies are out there, what language models are out there. And I'm just showing you here a screenshot from our forum where we have this ongoing whitelisting, where we wanted initially, when we started to run the competition, to allow contestants to only use language models up to a cutoff of 1st October. But of course, after the 1st October, all kinds of very interesting language models were released, and we kind of felt that contestants would have to fight with their hands tied behind their backs if we wouldn't allow them to use better language models. So we came up with this scheme of having contestants apply to whitelist language model. Then we check if this language model has a license that is sufficiently permissive to allow us to use the language model for scientific purposes. So in particular, we don't want a language model to be released under a license that is so restrictive that we cannot reproduce potentially the situation at the end of the competition or even later. So the license has to satisfy a certain number of minimal criteria that I'd collectively call open science principles in order for us to accept it. And here's just a selection of some of the models that we've whitelisted. And this is also kind of useful if you ever need to have a good model as a baseline that you want to further use for various mathematical purposes. You can just use one of the whitelisted models that scored highly on our competition. So that's one further takeaway, a baseline set of models. And of course, such a competition is an uncontaminated evaluation of state-of-the-art open-weight language models. And contamination generally is a problem with data and language models, and this is also present when we have mathematical data sets, and there are already papers that show that contamination exists in all kinds of language models. So having every once in a while a benchmark that gives you an uncontaminated evaluation of various language models kind of helps to assess how we really stand and where we really are. So running these competitions fixes a bit the contamination issue, but it doesn't fix other issues. And there are all kinds of other issues with mathematical data sets that remain. And one issue is that abstract mathematics is typically ignored in these data sets. So almost all data sets stop at high school level or university level mathematics. And when it comes to university level mathematics, almost all stop at, I would say, the level of an engineering degree in mathematics, or at most the first year undergraduate level in terms of mathematical sophistication. And there are a few exceptions to this, but really I think I can count them on one hand. There's the natural proofs dataset by Wellek, and essentially there's my dataset from 2023 that were the first ones that kind of broke through this barrier in terms of abstract mathematics. And I'm just giving a quick overview of what this evaluation brought to light, which we did on 3 versions of ChatGPT. And the dataset where we carried out this evaluation consisted of approximately 700 data points, which spanned different levels of difficulty, different types of questions. And in particular, we also tried to go a bit beyond just the first year, beyond the level of a first year curriculum in mathematics, which is here represented by the book by Walter Budin on functional analysis, chapter 2. This is something probably that we would study in a second year or maybe in a third year, depending on which university you use as an example. And as you can see, solving hard problems with tricky proofs, represented here by the Olympiad problem-solving subset of our dataset, is similarly hard to solving very abstract exercises, because exercises from chapter 2 are scored similarly low as Olympiad problem solving. This, of course, is not really up to date because this paper was released in 2023 and a lot has happened since. But from my understanding and just trying out working with language models on mathematics, frequently it seems that while both scores are better compared to 2023, the ranking among these data sets has not really changed much. So another issue that datasets suffer from currently is that there's only a binary evaluation. So that means you prompt the language model gives you an output, and then you say, okay, it's correct or it's not correct. But I contend that this is perhaps not the best learning signal that you'd want. What you'd rather want is to annotate your outputs with error codes. And here you can see how a sample data point looks like from our GHOSTS dataset, where we have the prompt, we have the output of the language model, but we have a rating, but we also have these error codes here represented by E5_2 and E5_4, and I'll show immediately what those are on the next slide, and some warning codes, which in this case we are not existent. And these error codes are essentially labels that show you not just that the language model failed on this particular prompt, but also how it failed. And it's a much better practice to compute a binary evaluation from the error codes rather than just giving a binary evaluation. Because one thing that you can do, this would be the warning codes, by the way, which are not errors, but still behaviors of a language model that you would not want it to have. And one reason why this is a good idea is that it helps you to understand on different parts of mathematics in what way your language model is failing. So you can then address this issue and perhaps create a specific data set so you can fine-tune your language model so that it stops making this particular error. If you just get yes/no response, you don't really know on what you should fine-tune it on. And here you can actually see from this heat map quite clearly, if you look at problems that are of Olympiad problem-solving type, so low abstraction, very tricky proofs, almost all error codes and warning codes are present. So in this case, it just means that the language model is really, really bad and cannot really understand what is going on. Although for other subparts of our data set, you can see that only a few error codes are present. So when you, for example, use the language model as a search engine to do retrieval, only a few error codes are present, so you can kind of zone in on those. Or if you want to focus on, let's say, topology, there's also just a specific 6 error codes that are present, and you can again zone in on those. So what further issues are there? Well, assessing a language model so that you can assign an error label works for the normal language models. But now, since essentially January, we have language models that think ever since DeepSeek R1 was released. And the problem with these types of language models is that their output is extremely long. So, for example, I evaluated the 10 reference problems on our AIMO 2 problems. And DeepSeek outputs in total almost 150 pages of output for 10 problems. And this is such a size of information that you'd have to process as a human to be able to give the correct label that this is just something that you cannot do anymore. In a way, it means that the language model that thinks will outscale you. You cannot really, especially when it comes to evaluation that requires experts, really be able to annotate the outputs of such language models. And if you inspect them, this is the output of the distilled version of the QN 32 billion model. You can see that the language model is kind of moving in circles. So it has a few select ideas that it kind of tries, and then it kind of oscillates back from them, tries a few things, then returns again to the idea that it already had a few pages ago. So it's kind of going sometimes a bit in circles. And again, this shows how tedious it is. So these lines that are in red here were manually annotated, and there is currently no good way to really do this automatically. Of course, you can ask another language model to summarize and so on and so forth, but that also doesn't really work well. So in a way, we are now in a bit of a corner with these thinking models, because training, as we know, is a deterministic black box. But at least previously, we could inspect inference humanly and be able to unambiguously determine what happened. And now we cannot do that either. In a way, inference has also become a black box, and we need to develop new tools to inspect these reasoning chains that thinking language models do. And I don't have an answer here. I'm just kind of pinpointing the problem. So in my roadmap of where this entire talk is going, we've now spoken about the math word problems, even though some of them may have really hard proofs. And now I kind of want to pivot into a slightly different direction, which is also an issue that current datasets have. And the issue here would be that we don't want, as mathematicians, to only deal with math word problems. We want a much richer behavior from a language model. We wanted to find counterexamples. We wanted to formalize a piece of natural language mathematics to Lean or Isabelle or Rock or some other interactive theorem prover. We wanted to help us to find all kinds of, let's say, relationships between mathematical objects, to do certain computations for us. So really rich behavior is what we'd want from a mathematical copilot or mathematical assistant. And this is where the remainder of the talk will be focused on. And it's good in a way to try to categorize the AI models that we currently have that can help us to do mathematics in 3 categories. So one would be really highly specialized models, such as alpha geometry, or the successor to at least the first alpha geometry, which is called Euclid, or models as the ones that are based on supervised learning that I've talked about in the beginning, that are based on the sampling approach to mathematics. So these highly specialized models all require you to understand their own formalism. You cannot just talk with them like you could talk with a language model. You have to read up the documentation. It's not so easy to use them. And they're also very narrowly tailored to a specific area of mathematics, and typically maybe not even an area of mathematics, but a single mathematical problem. And on the other end are the general purpose models, which currently are language models. And these are ones that have flexibility. You don't really need any particular training to use them, but they're still a far cry from a model that can really serve as a complete mathematical assistant and that is able to work the full pipeline of mathematical research, which encompasses these rich behaviors that I've previously talked about. And what we'd really want to do is we'd want to get from these general purpose models, the language models that we have today, towards these more fully automated models. And just to give you an illustration, let me play a video that shows Nuclid in action, which is a highly specialized model. So Nuclid has a GeoGebra integration, so you can draw a problem in GeoGebra. So this is your problem that you specify. Then you save it towards your Nuclid environment and you formulate a goal. The goal has to be formulated in a formal-like language, but it's still easy to understand. You want to prove that BA is perpendicular to BC. And after you've done that, you simply, here are two problems. We're solving the second one, the orthocenter one. You use the command line and Nuclid computes, ingests both the goal and the GeoGebra file. You wait a bit and produces a bunch of output files. And these output files show auxiliary constructions that the problem did, a formal proof, but it's humanly readable. It's not as hard as, let's say, full-on Lean or full-on Isabelle. You can kind of understand from this already how the proof would go. And what you also get is some metadata, as well as a nice HTML representation of essential information about the problem, meaning the various geometric objects that are present here, as well as their relationships among them. And what this showed is that you have this back and forth between different files, different representations. And to get to these fully automated models, what you'd really want is you'd want an LLM to be able to orchestrate this. You wouldn't really want to know how you'd have to use these various specialized models. You want to just tell a language model to use it and then to explain the output back to you, so you don't really have to click around. Kind of like this AI scientist already envisions. This is not something that is related to mathematics in any way, but it kind of shows the direction in which this would go and the direction in which you'd have to proceed to get something like an AI scientist. Of course, even this paper, they have a preliminary benchmark, but I think until we get to an actual AI scientist, it's still going to be quite a while. And to show how this could work, of course, Euclid was just an example from elementary Euclidean geometry. And I used Euclid, by the way, because while Euclid is built on alpha geometry does not have a GeoGebra extension. And I also want to say at this point, of course, I'm aware there are better geometric solvers out there, like Tong Geometry and Alpha Geometry 2. But these are not open source, which is a bit sad, I would say. So coming back, while Euclid showed particular pipeline for Euclidean geometry, of course, you also have in other areas of mathematics also all kinds of pipelines. And I'm just mentioning here one from knot theory. Knot theory has a very rich environment or ecosystem. There are all kinds of software tools that allow you to compute interesting things about objects that appear in knot theory. Mainly knots, of course, but knots are very interesting and mathematically rich and also computational objects. And kind of similar to Euclid, you also need a lot of domain knowledge to operate these tools, which is cumbersome because you'd, in some cases, not want to have to deal with the idiosyncrasies of each of the tools. And you'd want to run them in a more automated way. You'd want to make conjectures about relationships between knots. kind of like in the Nature paper from 2021 by Davis, where they found a single conjecture, or they found a single relationship and explored just a few conjectures. You'd want to really do this at scale in a much more automated way. And for this, unfortunately, data does not exist at all. So in a way, the landscape of data sets in mathematics is pretty bad because we constantly get more of the same. We get all kinds of variations of math word problems, but this is not really what we need at this point anymore. We need data sets to go in a rather different direction. We need data sets about what I'd call our workflows. And the idea of a workflow is just what I previously said, a sequence of steps that you have to do over and over again as a mathematician, that you don't want to tediously do with pen and paper, but you'd want to do at a single click, and you want your language model to know about this and be able to confidently carry out the workflow. And a good example of a workflow that is a few steps long is a workflow in ordinary differential equations that is very typical, where you're given a differential equation, and what you do is you find the fixed points, then you linearize the equation around the fixed point, and then, for example, you compute a stable or unstable manifold to kind of get a sense of how the phase portrait for the ordinary differential equation looks like. And this, of course, you can also connect with numeric solvers, but it's not something that language models perform really well on. And here we really, I would say, completely at the beginning. So we don't even have an evaluation set that tells us in a scientific, rigorous way how well language models are doing. We essentially have some scattered anecdotes on the internet where some people reported how well it did or didn't do. And that's kind of it. And similarly, a few other things that we'd like to have is abilities of language models to jump between levels of abstraction. So you're given an abstract theorem and you'd want the language model to be able to drop down one level of abstraction and see if there's a counterexample that you can find at that level, or the other way around. If you're given a statement, you'd want to see, can you generalize it to a more abstract level? And also what you'd want is you'd want the proofs that the language model can produce, such as for math word problems, simple university level mathematical problems, you'd want to be able to receive a so-called motivated proof. So this is a concept that was introduced by Polya in 1949. So it's not a new concept, but it was recently popularized, among others, by Tim Gowers. And the motivated proof is something where when you read the proof, there's nothing that just drops out of the sky. There's a certain inner connection between how you set up the proof. And this is also something that if you prompt the language model to carry out the motivated proof, it will fail pretty miserably. There are a few preliminary experiments that are in the paper that I mentioned at the beginning, on which this talk builds, that shows that language models still do not really have a lot of reasoning capability. And just to highlight, I've been talking about these in somewhat general way now, just to come back to the workflows for one bit, because there will be unfortunately not enough time to go into the second and the third point about abstraction, jumping, and better proofs. For workflows, another example from knot theory would be the one here at the bottom, where you have a pair of mathematical objects, you choose an invariant, you compute the invariant for the objects, and then you show that potential invariants are inequivalent if you want to make sure that these pair of mathematical objects are distinct in an isomorphic sense. And here what you'd really want to be able to get data sets of workflows is these individual 4 steps in this case. You'd want to represent as data, and you'd want to have natural language around these 4 individual steps so that you can get the language model to confidently speak about all the involved objects and all the involved operations. Of course, there are some issues here because the longer these workflows are, the more data sets you will need in order to cover all possible combinations between individual steps. So you have a bit of a problem here that the need for data grows almost exponentially. But at least this would be a first step towards getting language models to follow workflows. And there's also much more that should be done to get the entire landscape of data sets to a better level. For example, to collect data in real environments, because the way mathematical language currently is presented to language models is only textbook level language. But there's also an entire world of a different way of communicating mathematical language, in particularly oral communication. And this is something that should also be collected so that you can have the ability to interact mathematically in a more natural way with your language model. Another important thing would be mathematical data sheets, and I've just covered part of the data sheet here. There are more questions, but I just wanted to give you a sense of how these look like. And data sheets are this concept that you'd want every data set to have a data sheet, which is a standardized way that tells you what this data set really is about, how it was created, and so on. And there is a famous paper with, I think, almost 10,000 citations by now called Datasheets for Datasets. And these are generic questions that are important to have. And I think it's important to have a mathematical version of these data sheets for mathematical data sets. So you can, as the landscape of data sets grows, quickly see what this particular data set is about. And of course, there are many, many other things that we'd want to improve on in terms of how data sets currently are, such as better formal or informal support. And I hope that all of these things kind of gave you a glimpse into what needs to be done in terms of data so that we can hopefully in a few years have something that is what the GitHub Copilot is today for programmers. We'd want to have the Math Copilot for mathematicians. And this concludes my talk. I hope you enjoyed it. It's already quite late where I am, so apologies if I made some slight mistakes, but I hope overall I kind of was able to show a direction in which I hope the data sets in mathematics will move.
Thank you very much. Do we have any questions?
Yes.
Okay, yeah, no, interesting talk, very clear. So, I mean, to the extent, I mean, you gave us a lot of both practical and practical ideas to work on such things. I mean, it's the hope then that groups of mathematicians and perhaps collaborating with computer scientists will make these types of better data sets, and that will be a more, again, it's not like it doesn't happen, but it's really not a mainstream activity in the mathematical world. But
Exactly. Yeah, that's one of the main indirect goals, actually, that I would like to see happen more, to have mathematicians, in a way, engage more with computer scientists. And as you said, it's not that it doesn't happen, but I feel like it needs to happen more to make sure that we really get these math copilots, and also in a way to kind of make sure that some of the, I wouldn't call them mistakes, but perhaps detours that happened back in the 80s and 90s with the interactive theorem provers, that we can perhaps now avoid those. Because at that time, there were a few parallels to how things are now, I think. When, for example, Isabelle came up, or any of the other important big interactive theorem provers, there was this hope from the computer scientists that mathematicians would use them and that they would really turn out useful for mathematicians. And I think the computer science community was really excited about being able to offer this tool. But then it turned out that almost no mathematician really took it up. And interactive theorem provers only today, with the advent of AI, are kind of again entering the stage in a way, but now because we want to use them, for example, to do reinforcement learning with formal mathematics. And this kind of showed that there were a few friction points perhaps between the math and the computer science community. And I hope now, with when history perhaps won't repeat itself, but it rhymes, as they say, that this can perhaps be avoided now. And there is a stronger collaboration between computer scientists and mathematicians.
yeah, okay. I mean, that's of course we have a longer baseline of history of theorem provers, and the short answer to why mathematicians didn't use them more is they're not good enough, and the sense in which they're not enough is that they're too hard to use for, in fact, for anybody. And Isabelle was even limited in its expressive capabilities. A simple type theory just wasn't good enough. And Lean and Koch are not limited in that way. They're definitely a step forward, but they're still limited in their automation. It's still too clumsy. And it's just, things that intuitively should not be so hard, take much harder. And I definitely think that the progress in AI will change that over the next few years, and that will remove the barrier, and mathematicians will be using lean and comparable systems a lot. But now, when we come to the project that you're proposing now, so I mean, again, there's benchmarks people make in lean and so forth, but I agree with you that that's only one type of mathematical activity, and problem solving is one type of mathematical activity. And one wants to think of mathematics as a much more, if not unified, at least multifaceted activity that has these several tasks that always come together. And that's what I take as the type of benchmark that you're hoping for, something that has these workflows that involve several tasks. And so I think that's inspiring idea, but let me, one pushback that one could make, of course, is I think if you step back, there are parallels. They're not the same to do math and to do programming, but there are many parallels. And one might make the same recommendation for the development of programming copilots, that the programmers, the computer scientists should step back and make broader definitions of the task of programming. And it's not just writing code, of course, there are many activities that go along with that. And so far, at least in the published literature, people don't seem to be proposing that. So would you say that the analogy is flawed, or would you say they should be proposing that, or how would you react to that?
Yes, for sure. But I feel that computer scientists, in a way, are a step ahead, because, for example, there are these competitions on Kaggle, actually, also really big now, to see how many GitHub issues, for example, can be closed automatically by LLMs. And this would be one of those kind of workflow things, but for the programmer now, where, closing GitHub issues on all kinds of projects is something that the programmer does on a daily basis if he works in industry on some software. And computer scientists already have these benchmarks and data sets where they assess language models. Okay, how well can they actually do on these more real-world tasks? And we as mathematicians don't really have them yet. And I feel the very next step, and this is something that I'm also very interested in and already brainstorming for my next projects, would be to at least come up with an evaluation set. So never mind a training set, right? That's much more costly and difficult to make, but at least an evaluation set, so that we can see, for example, in terms of workflow execution or abstraction jumping, where do we stand? Like, how well or how bad do language models actually perform? So I think that would be like the immediate next step to do, to just, get this research effort started.
So evaluating not just solving a problem, but a series, again, a connected series of tasks that accomplishes some large goal. That's the kind of evaluation you have in mind.
Yes.
I would be interested in discussing that. I do think that is a worthy thing that hasn't so much been proposed in math.
Yeah, for sure. I mean, very happy to schedule perhaps a talk about that in the near future. I think really that the whole landscape of data sets in math also suffered a bit from the fact that in the beginning there was a good success with these math work problems, and then a large part of the machine learning and computer science society jumped on that and made almost any possible data set. But this won't really advance language models for the purposes of a mathematician. And I think any effort that goes more into the direction of the things that are listed would really help.
And there's another dimension that I don't think you explicitly broke down, which is, one way of saying it is just, how much training data, so obviously high school math, there's everybody learns that there's this vast amount of training data, early undergraduate, say linear algebra or simple problems in algebra. There's enough training data out there that
Yes.
that continue to be the objection. But again, most research topics in mathematics is not the case, for a variety of reasons. And
yes, exactly. And This is so in the slide where I said data collection in the real environment. This is kind of what I hinted at, but I kind of didn't want to have too many slides. And the issue is exactly as you said, right? We have so much data about undergraduate level stuff, but when it comes to research level mathematics, a lot of things are just communicated orally often from supervisor to student or among students. And the
So maybe you know the answer. I mean, again, there are, of course, mathematicians have always used libraries and have always, part of their education to become a research mathematician is to become familiar with one or more parts of the literature. And to what extent has it all been digitized? I mean, has the, there must be, math libraries tend not to be that big, actually, thousands of volumes and thousands of journals as opposed to, tens or hundreds of thousands. Has a lot of that been digitized? Has very little been digitized?
But even beyond that, like even let's say assume everything would be digitized. Even in that case, there would still be gaps in terms of data because there, for example, a common problem is the standard techniques that you use in a certain mathematical area. And for example, for PDEs, right, you have a long list of tools that you use and a lot of high-level intuition that you develop, and that is often passed on from a supervisor to a student, where the supervisor kind of tells you, oh, there's this good technique hidden in this paper where it's less about the particular proof. But
it's true, that may be how one initially learns it, but it's almost each point is in there's at least one research paper. It may be 50 years old, but that explains that technique.
Yes, but it's implicit often. So it's not explicit where you could say to a language model, this is like the proof technique. It's like, okay, here are a few examples that instantiate a specific proof technique, but no one's, and this is interesting data, right? That we want to train language models.
And they would figure it out. So again, I'm kind of not pushing back on this. I'm just, I think the biggest difference is just that there's for the easier mathematical topics, again, since there's practice so much more, there are many variations on the same thing out there, which are in the training corpus. And that's definitely not true for research level mathematics.
Yes. And there's also the problem of extracting that you touched upon earlier. That's also a tricky problem. So just to give you an example, I'm part of Numina, the nonprofit from Paris, whose model won the AIMO prize. And I've since started to collaborate with them, and we're working on an effort to extract mathematical data from a lot of PDF files that we find on the internet. And this is very hard, actually, because the essential data points that you want to have that contain a good mathematical learning signal are scattered, and it's very hard to make sense automatically of the core mathematical content in a PDF, because you have all kinds of information typically written down in a PDF that you don't really want to have in your final training data. And to do that automatically, to extract this mathematical core information from a PDF file, you need already a language model that can reason really well, much better than the current language models can. So in a way, you're kind of have a chicken egg problem a bit there. You want to have a language model that can reason better so you can extract better data, but to extract better data, you first need a language model that reasons well. Or you just do it manually, but that's of course not feasible at scale. So, we're talking here about millions of PDF files. So even the data extraction point, even if you have, let's say, everything super explicit in some journal, even for research level mathematics, even extracting it from a PDF file can be a bit tricky in some cases. And then there's also a lot of issues, and this really is manifested primarily for formalized mathematics, that the definitions don't always match. For undergraduate level, the definitions have been sufficiently polished and cleaned that they're essentially, you have like a worldwide standard of definitions. But once you reach research level, there, small variances appear, and especially in more abstract areas, some people consider something to automatically be commutative. In some areas of abstract algebra, in other cases, you have to explicitly mention, okay, this thing is commutative because the standard word doesn't include commutativity, and then you have to figure out from the context, which is which. And all of this makes essentially creating data sets with a high quality mathematical signal more or less a nightmare, I would say. So this would also be an example of a really interesting evaluation benchmark, just to see if language models at all can disambiguate from context which types of definitions are used. Because this is also often confusing for people.